This video is the fourth day of our Extra Topics chapter for Physics AP, and we're going to be taking a look at something called black body radiation. And in a simplified sense, this is all about the fact that when things get hot, they start to glow. In fact, I'm going to put exactly that down here right off the start. Black body radiation is nothing more than this. It's just the fact that hot objects like a stove element or coals in a barbecue or maybe some lava, hot objects glow. Now we're going to really focus on the colors that you see when they glow, but if you're wondering, yeah, well, why do they glow? Here's a real simplified explanation. The atoms on the surface of that material are going to be giving off some light because they're so hot their electrons start to wiggle. And when their electrons wiggle, they are accelerating, right, as they wiggle back and forth, and an accelerating charge actually radiates light. So as the electrons on the surface of this atom wiggle, they're able to radiate off light towards us, and that's what we see. But let's take a look at the different colors that you get, because one of the things that I've seen before is how when things start to really increase their temperature, the color that we see coming off as they glow shifts. You know, if you were to look in a foundry at some hot metal, actually I'm going to dare to only call this metal here warm, even though I definitely wouldn't want to touch it, but it's kind of got this reddy hue to it. And then if I get to the temperature of maybe some sparks coming off a grinder, well, they're now full on hot. They're a different color. They show up as very white. Or if I were to look at some stars out in the night sky, some of them are blue. And it turns out those blue stars are very, very hot. So let's try to figure out exactly why we see those colors. And this is a pretty common graph to see, and it shows how much light, the intensity, how much light comes off of an object that's heated up based on its temperature. And you can see the different colors showing up here, like how much light comes off in the blue area, the green area, the red area of the spectrum. And you can see it's actually got several graphs here for different temperatures of your black body. What's interesting is that when physicists were first trying to figure this out, and they were first running the math for this, before they had the idea of quantum mechanics, when they were just using what we call classical mechanics, the math for this did not predict these curves. In fact, let's take this blue graph here for this 6,000 Kelvin object. If you were to actually look at what the original math said, it would follow this curve up as it goes to the left, but it wouldn't drop off. It would actually just keep on going up like this, just steeper and steeper and steeper. And so I'm going to put a little note in here. I'm going to encourage you to do that as well. That curving up graph as you go to the left, that's what classical physics suggests. So let's say this, classical, pre-quantum mechanics, right? That's what we mean by classical. Classical physics predicts this curve. And clearly it doesn't follow that. It reaches a peak and then it drops off. So one more little thought in here, just kind of emphasizing that classical issue. It was Max Planck who first came up with the idea of these little packages of light all having the same amount of energy. So we're talking now with this classical physics about the time before Planck's work. So before Planck, before him coming along and saying, oh yeah, the little packages all have E equals HF amount of energy. Before that, we thought that objects would have now I want to just talk about the amount of color coming off. Okay, looking at that picture, looking at that pink line, really aggressively tall in the kind of purple end of the rainbow, dropping off a bit for blue, dropping off for green, dropping off for red. So we thought that glowing objects would have more purple than blue, more blue than green, and more green than red. But the actual picture is more complicated than that. The actual picture, it has these peaks. these maximums in the graph, right? And they've kind of been highlighted on this graph here. And it turns out this lambda at maximum, this wavelength where you hit your maximum and your peak, that's basically the color that you would see with your eye. So when you stare at an object, if it's fairly cool, you might see it as a redder picture. If it's really, really hot, then you're going to see it as a bluer picture. Now, I've got actually a little applet here, or one of those Fed apps where we can check this out. But before we do, just going to highlight this bottom axis on the graph. Right now, and this is probably the most common way to draw the graph, right now we've got wavelength for that bottom axis. And the wavelengths grow as you go to the right. Okay, so this is worth a little note here. Going to the right, we have increasing wavelength. Physicists often draw this graph with wavelength because wavelength is really all about the color, and that's something that we can directly observe. So it kind of makes sense to say, hey, let's draw this based on what I can observe. But let's talk where frequency would fit in. Frequency and wavelength are reciprocals, right? Frequency is really important for quantum mechanics because it's all about the amount of energy that's in the quantums of light. So going in the left direction for this graph would be increasing frequency. And energy, right? Because E equals HF for photons. In some sense, it would make more sense to draw this graph reversed, right? With frequency going up along the bottom instead of wavelength going up. But this is kind of the classical way that people tend to draw it. Now I've got one more little note that I'd like to add just down here at the bottom of this, but I'm going to do that after we've played around with a little simulator here. So this is one of those FET applets where you can actually simulate an object that's getting hot. And right now I have it fairly cold with my little thermometer that's here. And on my graph, I can see how much light of each color comes off. And there's a bit of red, and there's a lot of infrared that I wouldn't be able to see with my eye. And this blue BGR is blue, green, and red, little receptors for your eye or for a computer monitor. And it shows how your eye receptors would actually be stimulated here and then what your brain would sense the color to be. So kind of a dull orange for that temperature. It's quite cold. And I'm going to start increasing the temperature now of this object. Two things to notice. The graph just overall is going to grow, right? It's starting to actually get to the point where I'm going to have to rescale it. But that peak is moving. Now the peak is actually getting pretty close to the red end of my vision. And the color's switching. It's a little more orange, right? So I'm starting to see greens and reds in there. I might have to just scale this a bit. Now let's get it even hotter. Okay, we're going to go to higher temperatures. Okay, so notice that this is almost like an orange, getting a little bit towards the yellow now. I'm going to keep increasing the temperature. Graph just keeps growing up, but the key thing though is this peak is moving left. It's moving towards the blues. All right, I'm going to scale that down a bit again. I'm going to get close to the temperature of the sun. Okay, so 5,000 Kelvin, okay, around 5,500 Kelvin. We're getting close to the sun's temperature. What's interesting is this peak is now right in the middle of the Roy G. Biv spectrum, and we're seeing this now as kind of a white light. It could be like a white star or a white spark off of a grinder. It is kind of interesting that we don't sense it as green. You know, maybe we should, but we kind of sense it as just plain old white. We'll talk about that maybe in the tutorial. Now, if I keep increasing the temperature, then I start to end up moving towards a peak in the blues. And if it's hot enough, yeah, if this was a star and I was to look at it through a telescope, then I would actually see it with this nice little blue tint to it. And so that graph has grown and grown and grown. It's gone up the page, but the peak, the little color sensing peak, is actually moving left at the same time. So let's make a little note of that here. Okay, so as these objects get hotter and hotter and hotter, right? Maybe we'll say this, hotter objects. Okay, what happens when you heat them up more and more and more and you start comparing them to simply being warm? Well, a really hot object emits more overall light energy, for one. And the peak moves. So a hotter object will have a bluer peak intensity. Okay, so that's blackbody radiation, simply heating up a material and having it give off some light because its electrons are actually wiggling back and forth and accelerating and causing some radiation to come off, some light radiation to come off. Second page of the day, let's take a look at neon signs. You know, those nice colorful signs you sometimes see downtown. It could be like a nice open sign on a store. You know, exactly what's going on with those things there. Well, turns out to explain these neon signs, you really need to be thinking about quantum mechanics. I'm going to be just thinking about something simple. Let's go with maybe a hydrogen atom. So for a hydrogen atom, you've got a nucleus in there of a proton. Okay, so there's my little proton in the nucleus. And then there's a single electron that's orbiting around. But it can actually orbit around in a few different orbits, a few different locations. One option is to go to its simplest state, what we sometimes call the ground state, and it might be an orbit that's pretty close to that proton. Or it could move up to an excited state, an orbit that's a little farther away. Okay, so let's draw a couple of hydrogen atoms here. Draw another hydrogen atom over here, and it also has its ground state orbit, where the electron can fly around there, or an excited state. It actually has a number of these excited states. But the key thing is that single electron might be in the lowest state, that simplest state, where it's orbiting here, or maybe for some reason it's been elevated up to a more energetic state and it's flying around maybe in that second orbit. And there are quite a few, as I said, orbits that it can actually be flying around in. All right, well let's look at a little simulator here again from the PhET group where we can see how this deal works. So this is one of those neon tubes, right? This would actually be a hydrogen tube. And in it are some hydrogen atoms. Right now this particular picture has only got a single hydrogen atom. And we've got some plates on the end that are attached to some electricity. And we're going to be actually bombarding this atom with some electrons. And we're going to, as we do that, cause the electron inside that hydrogen atom to elevate, to get knocked upwards into a higher orbit. Right now, the little 1 tells me that it's in the lowest, simplest possible state. And I can go and fire an electron at it and watch it go up to a more elevated state. So let's give this a little shot here. I'm going to fire a single electron at it and just watch and see what happens when this electron goes in there. Okay, oh, it's causing it to actually give off some light. Now let's crank this battery up a little stronger here. Let's go for like even more. Let's go to like 30 volts here. So I'm going to fire an electron in again. And as it does, the electron inside this hydrogen atom is going to get elevated up to a higher state, and then as it comes down, it's going to give off some light. Now over on the right is this energy diagram. This level here is the simplest possible state, where the electron in this hydrogen atom is as simple as it can be in the lowest possible energy state. And it could go into the second orbit, the third, the fourth, the fifth, and the energies of those are all a little bit higher than each other, right? Until you basically get to the point where the electron is knocked free, which would be up here somewhere. Now I'm going to put this onto a continuous picture where it continues to fire electrons at it. And as it does, you can see that it's knocking the electrons inside this atom up to higher states, right? It's going to go from 1 to 6. And then the next time, maybe we go from 1 to 3. Now over on the right, you can see what happens when you have an elevated state. Now that electron can go and fall back down. And as it falls down, it gives off light. It can do it by falling down in several steps. It could go like from 6 to 5 to 2 to 1, or maybe right from 6 to 1. And as it does those drops, there's some very specific amounts of energy that are coming off, and so you get some very, very specific photon colors being released. Now this is kind of slow. Let's speed up here a little bit. Okay, so we're going to be firing lots of electrons at this thing. And you can see it getting excited and then dropping down into lower states. And every time it does, all of these drops have very specific amount of energy drops to them. And so you see some very specific colors come off. There could be this purple color. There could be a red color, right? Or there could be kind of a turquoise color that comes off. But there's some very specific colors that come off, and only those specific colors. Now, we don't have just a single hydrogen atom in there. Usually in these discharge tubes, these light tubes, we have many atoms in there, all being bombarded. And so you could fire a single electron at it, right? And it might hit one of them, right? If I fire one. Okay, great. Goes and hits an atom. Fantastic. But what if we have it on continuous? So we're just continuously bombarding all of these atoms with some electrons. You can see all the little numbers changing from ones up to different values. Let's go back to slow motion for a second. And as those hydrogen atoms, those are the big circles, as they go up to these elevated states, then those elevated states won't stay there forever, and the electrons drop back down. And as they drop, they give off very, very specific colors of light. And based on the colors of light that you see, you can look back and go, oh, I know that that must be this gas. That must be hydrogen, or that must be helium, or that must be oxygen. What you can do is you can put in what we call a spectrometer, where you can actually watch the various colors. You can split them, okay, probably using a prism, and then you can actually see the different colors that you get. And we often call these the lines of the spectrum, because in the device, when you stare through it, you actually see the colors split into these lines like this. Okay, so I'm going to turn the slow motion off, and then we'll see the spectrograph develop here. And so this is the spectrum for hydrogen, right? It's got this deep purple, a dark blue, a turquoise, and a red. Some colors you can't see, some infrared and some UV colors. I'm just going to pause this here for a second. So really what we're seeing are some specific colors off that specific gas that happen when the electrons in those atoms are excited up to higher states and then collapse back down. They make their way back down to the ground state. And there are only very specific energy drops that are available for each atom, and that's why we see some very, very specific colors. Okay, so let's make a little note here. First thing, we've been talking about these emission spectrums, where gases give off light once they're excited. So one key thing to note as a physicist is that each gas has a unique spectrum. Now the continuous spectrum, that's what you would see from black body radiation. You know, if you just had a light bulb where there was an element in there that physically got hot, you run some electricity through it, what we call an incandescent light. The element gets hot, and then it gives off all the different colors. That's great. That's an incandescent light bulb. But now we're talking about a discharge light, where you actually excite some gas atoms and then let them relax. And you see this emission spectrum. Some very specific colors come off, right? So back here, right? Sorry, wrong spot. Try that again. Right here, we're seeing some very specific colors of light show up. You know, that turquoise, the blue, and the red. Okay, so that's the emission spectrum. And we often just call them the lines of color, right? So we've got lines of color on a dark background. That's what we mean by an emission spectrum. So we're seeing the electrons after they've been forced up because of a collision. They're going to give off some light when they drop back down. So I'm going to write that in here. Electrons, they're transitioning. They transition from one allowed orbit they're going to transition down to another allowed orbit. And this happens many, many, many times per second. Now, astronomers can actually use this kind of in reverse to figure out what gases are present on the surface of a star. When the sun is giving off light and the light's heading towards the Earth, that light has to go through some gas that's right, near the surface of that star. So there's some gas here, and that gas may actually work in reverse. The light from the sun, right, that's coming from here is going to try to get through that gas and make its way to the Earth. And as it does, if that gas is perhaps hydrogen, then hydrogen has these transitions at very specific energies. And if a high energy photon is coming from the sun, it might pass through, and then if it collides with that hydrogen gas, it could end up causing an absorption where the gas actually pulls in that energy, transitions up to a higher orbit, and then maybe re-radiates it in a different direction or at a different energy that we don't see. And we actually see these lines of absorption. We see the exact same locations, right? They're in the exact same position as what you would expect for the emission lines, but we actually see them now as being absorption lines. We see these black lines on that typical black body full Roy G. Biv spectrum. So for an absorption spectrum, these are black lines, kind of missing colors if you wish. That's exactly what they are. They're black lines on a colored spectrum. So what's going on there? Well, gas on the star's surface absorbs the same specific light energies. And by same, I mean the same as the emission spectrum. So you've got this black body radiation coming from the star. Star's hot. Electrons are wiggling, giving off all different colors. But some are preferentially absorbed by the gas. And then when we're sitting here on the Earth, staring back at the star, could be the sun or any other star we see, if we split that light up, we can actually see those absorption spectrums. We can see the colors that are missing. And if we know our gases very well, then we can look and go, oh, hey, there's some oxygen present, or there's some helium present, just by seeing what bands of color are actually absorbed. All right, last thing for this page here, we're going to take a look at something called matter waves. The old view of hydrogen, okay, kind of classical physics, pre-quantum mechanics, the old view that we would often draw in our chemistry classes, I'll call this old hydrogen. It had these two little dots. One was the heavier proton in the center, and the other was this electron, this little dot, this little particle, right, that was flying around that proton in the middle. Well, that's actually not really what's going on. Now that we know how quantum mechanics works, here's the better way to look at it. Here's the new hydrogen. Okay, so this is following the work of, I'm going to say de Broglie. I'm told it might be pronounced de Broglie, but I like saying de Broglie. Okay, he said, no, wait a second. There's actually this wave issue going on here, and the electron is not a dot. It doesn't exist that way. It exists as this wave, and it has to be in these very specific orbits in order for the waves to actually constructively interfere. So you wouldn't want a wavelength for this electron as it circulates around. You wouldn't want it to kind of mismatch like this. This would be bad. This can't exist. That orbit's not quite allowed. But this orbit here, this is a good orbit, right? That's an allowed orbit because the waves, by the time they come all the way around, they match up with themselves again. So you get kind of them constructively interfering with themselves, which is kind of neat. So some thoughts, final thoughts here for this day. You got to realize that these electrons, just like light, these electrons have wave-particle duality. They can exist both as a particle, but they can also exist as a wave. And it's their existence as a wave that explains these allowed orbits. So we have to be ready to calculate their wavelength. Okay, so this is their matter wavelength. And there's a neat little relationship that lets us do that. So their matter wavelength is given by this relationship. This is the wavelength for a matter wave. Planck's constant divided by, now we're not talking about photons here, we're talking about electrons, things that have mass. It's Planck's constant divided by the momentum of the particle. So just kind of thinking about our classic little checks and arrows, if the velocity grows, okay, that's going to make that denominator bigger, then the wavelength drops. Now for those hydrogen atoms, we saw when we were talking about those gas spectrums that there's these energy levels. Okay, so I'm just going to draw a little energy graph over here. And I'm actually going to put 0 up here at the top. This is kind of like what we were talking about with potential energy for planets, you know, that negative G_m_m over r, where 0 is kind of the goal to get all the way free. Okay, so this would be the level of a free electron that's managed to get away from that proton. And up and down here, I'm graphing the electron energy. The actual graphs are pretty easy to generate for hydrogen. You're going to have deep down here the lowest state, kind of the lowest possible orbit. Think of like Mercury going around the sun, right? This is orbit number 1. And then you work your way up. Then you're going to have the next one. They start to really bunch up. So I'm probably going to, this is probably very poorly drawn. Probably should have gone a little higher with that one. Okay, then they're going to get a little tighter. But if I draw them too tight, then they're just impossible to draw. By the time you get up to around 6 or 7, you're basically right near that free state, right? So you can see that, yeah, I've got this dilemma here, right? I wanted to draw them really tight together, but then I can't get all the numbers in. And then those electrons can get forced up into higher states. Like maybe they end up getting forced up into that n=5 state, but they won't stay there. They can then make their way back down. Maybe they make their way down by going down to state 2, and they'll give off a photon in the process. Or maybe they then go from state 2 down to state 1, and they're going to give off a photon in that process too. Now for this graph, the energies could be written in joules, but it's actually nicer to put them in electron volts. And somewhere down around here is like -13 electron volts. So to go from the usual ground state, as we call it, n=1, the simplest state, all the way up to free, to be knocked free from that atom, is actually only around 13 electron volts to do that. Okay, so that marks the end of this day's lesson for looking at blackbody radiation and then emission and absorption spectrums. Next day we're going to look at crystallography.